So the other challenge is phenology. And within phenology, there are kind of two sub-themes, spring and fall. So phenology is that, the timing of ecological phenomena. In this case, we're defining it as the greenness of the canopy or the redness of the canopy. And in the winter, a deciduous forest is not very green and it greens up in the spring. And that green up is what we're forecasting. And so this is effectively forecasting spring. And so this is daily forecasts of the canopy greenness at 7 deciduous broadleaf neon sites. And these are measured by phenocams, which take a picture every half hour. We use the middle of the day. And within that, there's regions of interest that are solely deciduous trees that are being forecasted. And in the fall, I need to change this. This should be redness. The fall, we're forecasting both greenness and redness because redness is really neat because redness spikes in the fall as greenness goes down, and then redness goes down as the leaves are dropping. And you can think about this as forecasting when is it best to go see the colors at this site. And that sub-challenge is beginning July 15th and runs through December 31. And so here's an example of the target data for the 7 sites. And you can see there's the phenology challenge is really exciting because it's got really great data coverage. It has low data latency, as in the data is functionally instantly available. And since it goes back in time further, there's more opportunities to build more empirically based models from this. And there's sort of clear seasonal patterns, and it really lends itself well to some time series types analyses as well. And so you can see here the greenness across the 7 sites. And here's an example of a team that contributed a forecast. This was that forecast generated at the beginning of April, and we can ultimately see how it turned out. This particular forecast looks like it did pretty well. It's pretty exciting to see. We'll probably underestimated the uncertainty a little bit, too tight a confidence, which will ultimately result in a higher score, which remember lower is better. But tracks quite well. So we'll get scored well on the, it'll be scored well on the kind of the precision aspect of it. And it's really neat to kind of see how we've been running the challenge long enough that forecasts now are completely able to be evaluated. And so some keys to the phenology challenge. One is it is the most real-time forecasting theme. And so it isn't a necessity, but it does challenge you to think about how to set up an automated workflow that just runs and submits forecasts in the background of your computer. That's the easiest way to contribute. Build a model and then have it apply the model as new data comes in, or whether your model updates or not, where it submits new forecasts every day, automated in the background. And the other kind of challenge associated with this is actually covering gaps in meteorology data. There's this kind of neon data becomes available, as I said, in these monthly packets. So there's going to be a latency in neon data. Other things that are out there that you could use, like the National Land Data Assimilation System that puts meteorology data, that has a 4-day delay. And then you have the weather forecasts from NOAA that run from now out 35 days, although we have them in the past. And so coming up with a way to kind of stack together the meteorological data out there. And it's important to be aware that NEON isn't giving instantaneous meteorology data. They will never give that. They're working on reducing data latency, but you shouldn't expect instantaneous weather data from NEON sites to build your models and to generate your forecasts. And so there's that constraint to work with. And we're working through, as part of this forecasting challenge, what are the best practices for kind of linking together a lot of these different meteorological data sets to develop both a historical and future representation of the weather at these systems.